beautiful people, and welcome. In today's video, we're going to be graphing cubic functions. And disclaimer time, if I make a mistake, that is okay. Just let me know where the mistake occurs, so that way we both can learn from my mistakes. Let's get started with the parent function. Now, cubic functions or odd functions, they all look a particular way. So for a cubic function, all of your graphs are going to look like this. We're going to go down this way. We're going to curve up and go up. Now in our class, we're going to mention that shape, that cubic curve, as Mr. John Travolta. And I don't believe he has an H in his name. And I'm just going to call him Mr. John T. So whenever you hear us saying in any videos Mr. John T, we're referring to this sort of curve. Now let's talk about end behavior. What is end behavior in general? Well, end behavior is what's happening at the end or towards the end of your function. Now, because this is an infinite function, it goes all the way up, all the way down. We just try to identify how it behaves. In this way, end behavior. So, when x approaches infinity and when x approaches negative infinity, something happens. So whenever you're writing end behavior, you're always going to start out with when x approaches infinity and when x approaches negative infinity. Now, when that happens, two things happen. This statement right here, when x approaches infinity, that is saying when x gets super duper big, all the way up to infinity in the positive direction, here's your x-axis. When x gets really, really big, what happens to your y's? So what happens to your y's? So if you recall, y is just another way of saying f of x, or f of x is another way of saying y. So as x gets really, really big in the positive direction, notice what happens to our y. Our y goes up, 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 all the way to infinity and beyond. So when x approaches infinity, y, or f of x, approaches infinity. And again, this is the end behavior for the parent function. And now we have as, oh, and then you know what? This should be a comma, not an arrow. The arrow represents approaching. So we have as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, again, that means when x gets super duper small in our negative direction, what happens to our y? What's the behavior? In this case, it drops down all the way because we have an arrow. That means it goes down to infinity and beyond. So then we have f of x, or y, approaches negative infinity. So that is the behavior of our parent graph. Now, for the reference points, for our parent function, there are 3 points that we need to be aware of, and we always need to know these reference points. So when we have a cubic function, I didn't do one thing, which I should have done from the very beginning, and I apologize. I graphed the parent function without even telling you what the parent function is. Shame on me. So let's go ahead. The parent function is f of x is equal to x cubed. This is our parent function. So this graph, this curve, came from me plotting points. What I did is I plugged in numbers in for x, and then I cubed it. So one of the pretty points you'll hear me talking about are the reference points. There are 3 reference points, or 3 pretty points that work for the parent function. Now, when we do transformations, these pretty points will be transformed. These reference points will be transformed depending on what we have in our transformation. So first pretty point is if I plug in 1 in here, so 1 cubed is 1. If I plug in 0 in here, 0 cubed is 0. And if I plug in -1, -1 cubed is -1. So you have 3 pretty points, or 3 reference points. Let's go ahead and see where they're at here. So I have 1, 2, 3, 4. So we have 0, 0, 1 and 1, and negative 1 and negative 1. So we have 1 and 1, which is here. We have 0, 0, which is here, and we have 1 and 1. So if you were to graph this, let me do that real quick. Do a quick sketch. This is why knowing what your parents look like is super important here. Because if I was to graph 1 and 1, 0, 0, and negative 1, 1, that looks like a line to me. If I was to connect it just straight, then that would be incorrect because we're dealing with a cubic function. But these reference points, the 1, 1, 0, 0, you're going to find that it's going to be very, very common for many different functions. However, you need to know that you're looking at the exponent or the highest exponent or the total exponent of the function, depending if you have it in expanded form or you have it in a general or condensed form. So if you're looking at the exponent, this exponent tells you the behavior, the end behavior, it tells you the behavior of this function. If this number is odd, if your total number is odd, or if the highest exponent in expanded form is odd, then you're going to have a John T, you're going to have a John Travolta, and it's going to look like a curve like this. So let me go ahead and connect my reference points or my pretty points. And remember, when you're doing this, you're going to go from the vertex or the middle point, go down, and then you're going to curve up. Make sure that you know that this is how a cubic function looks like. Let's talk about domain. Now, domain are all of the possible. Let's actually write that down because sometimes we struggle with domain and range. Domain are all possible x values in our function, and range are all possible y values in our function. So what that means is, what are all of the x values it can be? What are all of the y values it can be? Is there anything, what I like to ask, is there anything that it can't be? Because if we rule out what it can't be, then we know what it can be. I know it's a little confusing, but just focus on what it can be. So what can x be here? Is x anywhere on here that it can't be? In this case, x can be anything we want it to be. So domain, you can write this in different ways. What I choose to do for domain, I like it in this way. So we do a parenthesis, excuse me, means we cannot grab it. We cannot grab that number. In that case, we cannot grab infinity and we cannot grab negative infinity. If it was to end at, let's say, 3, if we cut our function, we have an ending at 3 and we can grab 3, then we would have brackets. But since we cannot touch infinity because it is infinity, then we use parentheses. I call this no touchy-touchy. And then for range are all of our y values. So what can y be? Is there anything that y cannot be? In this case, no. Y can go all the way up to infinity, like we said here, and y can go down to all the way down to infinity. So range, we can do from negative infinity to positive infinity. Now, you have to write this as such, just like you would on a number line. Your negatives on a number line, and then you have your positive. So your negative infinity has to come first and then your second. Another way that you can write this is you can say all real numbers. From negative infinity to positive infinity, we have all real numbers. All real number symbol is an R with 2 lines. And that means you have all real numbers in the domain and all real numbers in the range. All right, let's talk about formulas. For your formula, this one is going to be written pretty big, and I'm going to give you a few, not necessarily a few different ones. I'm just going to give you one, and then I'm going to condense it. So we have the general form. Let's write that out, general form. And this is the form we want our equations to be in, because then it's super duper easy to graph it from that, knowing that your translations and transformations. All right, so we have for our general form, if we have a negative a times b times x minus h, all of that is cubed, so we have a double parentheses, plus k. So let's identify that, and then we're going to condense it a little bit. So if we have a negative out in front, that's going to mean you have a reflection across the x-axis. If you have a negative, that means your function is negative and you're going to flip it across the x-axis. Your a value is outside of the bubble. Ooh, let's use a different color. Your a value is outside of the bubble. If it's outside the bubble, that means it is vertical. So we have a vertical stretch or compression, depending if a is a whole number greater than 1, or if a is less than 1, which is a fraction. Fraction would be compressed because it's outside of the bubble, it's small. Whole numbers would be a stretch. Now the inside bubble here, inside the bubble means we have horizontal. So let's do this one, horizontal. And this one here is horizontal stretch or compression. Now anything that's inside the bubble is always the opposite. So if you have a whole number for B, that means you have a compression. We're doing the opposite. If you have a fraction for B, you're doing the opposite, which means you have a stretch. Same thing for the inside bubble. We have negative H. Always do whatever's the opposite of H. So if H is negative, that means you're going to the right. If H is positive, if this right here, negative, if you see this negative sign, that means you're going to the left or you're going to the right. So this is horizontal shift. Depending left or right. And then the last one is we have this plus K. And plus K is outside of the bubble, so we do exactly what it shows. In this case, we have a vertical shift. Now, vertical shift is up or down, and horizontal is left or right. So this is the general form. Let's go ahead and compress it. So one thing you're going to notice is, yes, we can have a B out there, and this B is cubed. So what really happens when we have this general form, a lot of times the horizontal stretch gets absorbed by the vertical stretch, okay? So if you stretch something enough, up or down, left or right, there is also going to be some horizontal vertical stretching that occurs. So if we can absorb the horizontal stretch, that is one less thing that we have to worry about. So let me go ahead and show you how that's done. I'm just going to do a thinking bubble here. This is just our thinking bubble for me to explain how that happens. So let's say we have our general form. I'm going to leave out the negative because I want my form to be positive for this example. We only need to concern ourselves with the negative if we have a reflection across the x-axis. Okay, so notice how I have this cubed in a bubble. So this means I have A times B cubed, and I have x minus h cubed. Now I can do this only because I have multiplication. Now do not do this way here when you have subtraction. Totally different. You can only do this when you have multiplication. That means I have a times b cubed and I have x minus h cubed. This right here is the same as what is here. Now let's pretend b is a number. Let's pretend b is 2. 2 cubed, 2 times 2 is 4, 4 times 2 is 8. So 8 is just a number out in front. And let's say A is a number as well. Oh, I don't know, let's say 3. If A is 3 and B is 2, and they're just being multiplied together, this can be combined. It's just a number times a number. So combining that gives you, and I'm going to call this is A1, let's call this A2. So combining this will just give us another number. And this A is now being multiplied by x minus h cubed plus k. This formula looks a whole lot simpler than what we originally had. And that's the formula that we're going to use, this one here, for the majority of our graphing. Now you do need to understand that there could be one in a form like this with a horizontal, but most of the time you're going to see something like this. All right, so let's rewrite our general form to the one that you're going to be using most of the time. And so what we have for our general form is this one right here. We will have f of x is equal to a times x minus h cubed plus k. And you need to know that a is your vertical stretch or compression. X is just a variable. We keep that. H is your horizontal horizontal left or right. K is up or down. Now there is one other thing that you need to know, and that is where your vertex is. Now vertex, see here, your vertex is your middle point. So where the change happens. So when we have let me actually write down what the vertex is. It is h comma k. And it is the opposite of whatever you see. So if you see a minus h, you're going to do a positive h. Okay, so you're going to do the opposite. You want just the h without the symbol. So if you're looking for the symbol, it will be the opposite. And we'll do an example of that. So we want the vertex. Here's your graph there. And vertex is h comma k. You can kind of go without the vertex. We're going to use more of the vertex when we are writing equations versus graphing the equations. All right, let's go ahead and get started on an example. We're going to do one or two examples on this one. I understand this video has now become a little bit on the longer side. Oh, I didn't explain what a vertex is. So if you have your parent function here, and this part goes down, so your end behavior goes to, so your y, as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity, and that's that change. Your vertex is that change from going to the negatives to going to the positives. It's that middle, I call it the middle of the middle. So it's the middle right here for your changes for your vertex. Okay, let's do a quick example. Example number 1, we have g of x is equal to 2 times x minus 1 cubed minus 1. We know that we have our parent reference points. So we have our reference points. And you need to know what they are. Now, if you don't remember your reference points, just know that your parent function for this right here, see the exponent of 3, that's cubic. So that means your parent is x cubed, and you can plug in pretty numbers in there to figure out what your reference points are. But it's going to be 1, 1, 0, 0, negative 1, negative 1. That's your reference points. We're going to use the reference points to figure out what happened to them. So let's do our translation. Notice I have a 2. If I have a 2, that means, oh, you guys can't see. Let's zoom in. If I have a 2, that means I have a vertical. It's outside the bubble. I have a vertical stretch by 2. I have a negative 1 on the inside. That means it's opposite. So I have a right 1. I have a negative 1 on the outside of the bubble. So that means I do what it's saying. So down 1. So vertical, here's a thinking bubble. Vertical affects your y. Horizontal affects your x. So let's see what our changes, oh, you guys didn't see that. Let's see what our new x and y are going to be. And I'm going to show you this in one way, and then I'll show you the other way, because you need to know what happens to your 3 reference points. So here's your horizontal. Here's your vertical. So what happens to your horizontal something, your horizontal x? Here's your x. So I'm looking at my translation here and I'm trying to see if there's anything that's horizontal. So I have a vertical stretch by 2, so I don't have that. I have a right 1. So horizontal is left or right, this way, right? Horizontal is left or right, vertical is up or down. So if I'm going to the right 1, that means I do have a horizontal change. And I'm jumping once to the right, so I'm doing the opposite. So I have a +1 for my horizontal shift. Now let's look at the vertical. Is there any other horizontal? There isn't. I do have a vertical stretch by 2, so here's my y. I do have a vertical stretch by 2, so if I have a vertical stretch by 2, I do what it's telling me. It's outside the bubble. It's telling me to multiply by 2, which I'm going to do. So I'm multiplying by 2, and then what's happening here is I also have a down 1. So that means I have a vertical shift, a jump, vertical jump by 1 down. So I'm going to subtract 1. So this is now equal to your secondary x, and this is now equal to your secondary y. And the secondary x and y, those are your new reference points. Those are your new pretty points. You only need 3 to graph. And once you have your new pretty points, then you're able to decide what is next. You can also do this just by graphing, and I'll show you again in just a little bit. So let's go ahead and do that. This x is your original. So I'm going to do like a bubble, and then I'm going to do +1, bubble, +1, bubble, +1. Here I'm going to do the same thing. I have, let's change colors just to be different. We have 2 times the bubble minus 1, 2 times the bubble minus 1, 2 times, 2 times a bubble minus 1. So when I say bubble, I'm just leaving some parentheses in order to apply my reference point. So the first reference point is 1, so I'm going to plug in 1. Second reference point for x is 0, and then third reference point for x is -1. So 1 plus 1 is 2, 0 plus 1 is 1, -1 plus 1 is 0. These are my new x values after the transformation. Let's do the same thing for y's. Here's 1, 0, and -1. 2 times 1 is 2, minus 1 is 1. 2 times 0 is 0, minus 1 is -1. 2 times -1, that's -2, minus 1, that's -3. Here are my new y's. So now we're going to take these points. So new points are 2, 1, 1, -1, and 0, -3. Now that I have that, I'm going to go ahead and graph my 3 new reference points. Oh, you know what? Let's do this. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. Let's graph our parent and just see what the difference is. And I'll show you actually a different way to graph this as well. It's pretty cool. So let's do 0, 0 is 1. 1, 1 is another one. And then -1, -1. Again, be careful. This is not a line. Our highest degree or our total degree here is 3. 3 means it's cubic. Cubic means it's going to look like Mr. John Travolta. So we're going to go down and curve up. So let's do this. Let's apply. Do we want to? No, that's okay. So let's apply our new points to this. So I have 2, 1. I have 1 and -1. And I have 0, -3. So again, where's your vertex? Your vertex is h, k for your vertex. And that's going to be your middle point. You're doing the reference point, it's going to be your middle point. So from the middle point, you're going to connect, it's going to look just like this. You're going to connect down, and then you're going to connect up with a little slit curved in the middle. Now, it could go up a little bit more. You don't have to worry about the behavior precisely after your 3 reference points. You can if you wanted to. All you need to do is 3, and you've graphed it. Now, here it is. Here's another way of doing it. You have a vertical stretch by 2, so you know it's going to go wider. So your y's are going to multiply. If you're doing this, trying to do this without your reference points like this, it's going to be a little bit more difficult. Now, let's do the same example, just in a different way. what you can do, let's do this x3 and y3 just to let you know that this is another method. Notice that we have an equation. Here's our equation, 2 times x minus 1 cubed minus 1. All you have to do is, inside your bubble, for x, pick numbers. Like we're going to plug and chug. We're going to think this is pre-algebra, algebra 1, integrated math 1. So we're going to plug and chug for our x values and see what our output. So input is x, output is y. So input, if I want to do 1, because I think 1 is a pretty number, and the reason, now we're not looking at how they look. We're looking about what it gives me inside the bubble. If I put 2, I can absolutely do 2. 2 minus 1 is 1. 1 cubed is 1. And I can go from there. However, it's not going to be your reference point. So we want the closest things to our reference point. So let's do 1. If I type in 1, 1 minus 1 is, what do I have? 1 minus 1 is 0. 0 cubed is 0. 2 times 0 is 0. 0 minus 1 is negative 1. So if I plug in 1, my output is negative 1. And how am I doing this? I'm doing this. 2 times x minus 1 cubed minus 1. And I'm literally just plugging in numbers. So I'm saying 2 times what's pretty to make my inside bubble simple to solve. And I said, if I plug in 1, I know that 1 minus 1 is 0. 0 cubed is 0. 2 times 0 is 0. 0 minus 1 is negative 1. So when my input is 1, my output is negative 1. So there's my 1, negative 1. So we're going to do that a few more times. And again, choose your pretty points, choose your pretty numbers that make your inside bubble easy to simplify. Like if you wanted to do 6, you can absolutely do 6. 6 minus 1 is 5. 5 cubed is 125. Now, 125 times 2, absolutely you can do it, but it's not going to be the easiest thing to graph. So we're going to choose small numbers. We're going to choose numbers that give us pretty things on the inside. Another one that I can do is 0. If I plug in 0 in for my input, I know that 2 times, 0 minus 1 is negative 1. Negative 1 cubed, remember if your exponent is on and you starting out with a base that's on, it's going to be on. So I have negative 1. 3 times negative 1 times negative 1 times negative 1, that is equal to negative 1. Now I have negative 2 minus 1, that means I get negative 3. So when my input is 0, my output is negative 3. Now let's do that one more time. Another pretty number is, and I think I mentioned 2, so let's do 2, because I think 2 is pretty enough. So 2, my input is 2. 2 minus 1 is 1. 1 cubed is 1. So 2 times 1 is 2. 2 minus 1 is 1. So when my input is 2, my output is 1. And so then we have our points that we originally started out with. Here they are. Just an easier way to do it, just plugging and chugging. Now, however, if it's asking you to translate what happens to those points, you're still going to be needing to do this. So what happens? You move right once, you move down once, and you have a vertical stretch to be able to translate it. However, if you're graphing, this method, in my opinion, is much easier. Right here, plugging and chugging, making sure that you have pretty numbers. Again, pretty numbers. We're not looking at the way they look. We're looking at the outcome of putting the number inside the bubble in for x. So you want that to be a simple number. We want it to be small, closest to 0 as possible. All right, beautiful people, I'm going to go ahead and wrap up this video. Please spend some time practicing these. We're going to do lots of practice in class. If you have any questions, reach out. Transformations will follow you for the rest of your life in your mathematical career. Please make sure you practice. Thank you so much for watching my video, and I will see you in the next one.